welcome to the first lecture on Chapter 10. Today we're going to talk about Lewis structures and how to draw Lewis structures for molecules. So Lewis structures are 3D, well, this is a 3D one, but they're representations of molecules that we can draw on paper to show how the electrons are arranged in molecules. So first we have to talk about Lewis electron dot symbols. So this is a Lewis symbol. It's the easiest way to represent the valence electrons, which we show as dots when they're placed on the sides or the top or the bottom of the symbol for that element. So like chlorine, if we look on the periodic table, chlorine is a halogen. It has 7 valence electrons. And so what we would do is we would take chlorine and we would essentially think about chlorine being in a box, and we can put chlorine's valence electrons on the sides of the box. And the way that we do this is we put 1 on each side before any can get 2, and we just kind of go in a circle. So like 1, 2, 3, 4, 5, 6, 7. Now it doesn't matter where you start or where you end as long as you kind of end up going in a circle. So you see like here, this unpaired electron is on the left, whereas here it's on the right. Either way is totally fine, but regardless of which way you've drawn it, and by the way, don't draw the box, just make the box the imaginary box. But either way that you've drawn it, you have 3 sets of paired electrons. These are also sometimes called lone pairs. Okay, so we have 3 lone pairs or 6 paired electrons, and then in both of these depictions we have 1 unpaired electron, and the unpaired electrons are the electrons that are going to be available for bonding. So here, since chlorine has 1 unpaired electron, it's going to be able to make 1 bond. If we look at carbon, carbon has 4 valence electrons, so it ends up with 1 electron on each side, and it has no paired electrons, no lone pairs. So since carbon has 4 unpaired electrons, it can go and make 4 bonds. This is actually one of the reasons why carbon makes so many bonds and forms so many compounds. So here's a bunch of different Lewis structures that have been drawn. And again, remember, you're looking at the number of valence electrons to tell you how many dots are going to go around your symbol. And if you look at the noble gases here, they have 8 valence electrons, except for helium, right? Helium's kind of a special case. But otherwise, these noble gases have 8 valence electrons, and if you look, they have no unpaired electrons. This is the reason that we call them noble gases. They're too good to make compounds, right? They can't form bonds because all of their valence electrons are already paired. They don't have any unpaired electrons to donate to another atom. So there you go. So these molecules, right, we're going to write them for covalent or molecular compounds, and they're going to be represented by Lewis structures. The valence electrons of the atoms, the way that we do it is we're trying to give all of the atoms an octet, except for, hydrogen and helium. They follow what's called the duet rule, and they just want to have 2 valence electrons. But otherwise, all of the atoms are trying to get to 8. That's why atoms form compounds and molecules. It's because they're trying to have 8 valence electrons. So we're trying to follow this octet rule. The bonding pairs, so we're going to share electrons, right? We know in molecular compounds, electrons are shared rather than being transferred. And so when these atoms share their electrons, they form what's called a bonding pair. And we can show them 2 different ways. We can show it as 2 dots between the atoms because each atom is contributing 1 electron, right? So that's why we get the 2 dots. But we'll typically, so this is kind of like as a beginner, you'll maybe show them as 2 dots. And then as you get better at bonding, we want to show it as a single line between the atoms. So this would be like if hydrogen bonded with another hydrogen, right? Each atom has 1 valence electron. So here, a bond is being formed between those two hydrogen atoms, that 1 bond there. So 1 bond, 1 single line will actually represent 2 electrons. We're going to get lots of practice with this. And the non-bonding pairs, like I said, or they're usually called lone pairs. They'll be placed on the outside of the atom. So something like if two chlorine atoms were bonded together, we have the bonded pair in the middle, and the lone pairs are going to be around the outside. And I'll show you how to draw molecules like this as we go through. So here's fluorine. Fluorine consists of two fluorine atoms, and we know this because it is diatomic, right? It shows up in Hofbrinkel. Here's our fluorine. So fluorine floats around as F2, not just as F, because if it floats around as fluorine by itself, fluorine has 7 valence electrons. And since it doesn't have 8, right, it has this lone electron here that's available for bonding, and it's more stable for it to float around as F2 with that electron bonded up. Okay, so we'll see how we draw this. So here's one fluorine, and here's another fluorine, right? So if they were by themselves, and instead of being by themselves, they can share these electrons. And when they share these electrons, they form a bond, right? And so these are the electrons that are being shared. So now the fluorine on the left has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it, and the fluorine on the right has 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. And so by sharing those electrons, now both atoms, both fluorine atoms, are experiencing 8 valence electrons. So they now have an octet. This is why they float around as diatomics rather than as single atoms, so that they can achieve these octets. And again, rather than writing those these electrons in the middle like this, we'll replace those 2 bonded electrons with just a single line to show the bond. Okay, and so this would be how we would draw it. You show all the lone pairs and the electrons that are being shared between them. So the octet rule. Combinations of elements tend to form so that each atom, by sharing electrons, because we are in covalent, right, which is also known as molecular, so they're sharing in electrons, and they're going to get an octet in that highest occupied energy level. So they're going to have 8 valence electrons. So here is monatomic chlorine. So mono means 1, right? 1 atom of chlorine. And so again, chlorine has 7 valence electrons. So there's 7 dots shown around it. Here is diatomic chlorine. And we know chlorine is diatomic because of Hofbrinkel, right? Chlorine shows up in Hofbrinkel. And so since we have chlorine there, right, we know it's a diatomic. And when it floats around like that, it has 1, 2, 3, 4, 5, 6, 7, 8 electrons around the left chlorine, and 1, 2, 3, 4, 5, 6, 7, 8 electrons around the right chlorine. And so now they both have an octet. They are stable. And again, like I said, rewrite these 2 electrons that are being shared between them as a single line, and then fill in all of those electrons that go with it. So this is a table from your book. These are all of the atoms or elements that exist as diatomics. And again, my favorite way is to remember it as Hofbrinkel. So Lewis structures, drawing these Lewis structures will show the sequence of the bonded atoms in a molecule or polyatomic ion. They'll show kind of how they're arranged, and they'll show the bonding pairs, right? So the electrons that are being shared between atoms. And they will also show lone pairs, so electrons that are not participating in bonding. And it'll show the central atom that's bonded to all of the other atoms. Okay, so these are all the different things that Lewis dot structures will show. Sometimes they're also called electron dot formulas. Lewis structures is a little more common, but just if you see that in your book. Again, we're going to go through lots of examples. You're going to get lots of practice. Here are some examples of molecules. We're going to draw these actually moving forward. But if you'll look, correct Lewis structures, like this one, this is CH4 here on the left. And so each of the hydrogens, like the hydrogen on the top, has these 2 electrons, right? This hydrogen has 2 electrons, this hydrogen has 2 electrons, and this hydrogen has 2 electrons, right? Because hydrogens follow the duet rule. Hydrogens always want to have 2 electrons to complete their outer shell. Carbon in the middle follows the octet rule, so it should have 8 electrons around it. So we go 1, 2, 3, 4, 5, 6, 7, 8. Double check so that carbon has an octet. Okay, and the same would be true for all of these other elements. The hydrogens all have, all of these other compounds, the hydrogens all have 2 valence electrons, and nitrogen and oxygen, respectively, both have 8 electrons around it. Okay, so that's kind of the whole goal when we draw these Lewis structures. So here's some rules to help you out, and like I said, we're going to go through lots of examples. This I would maybe print out or write down so that you have it for reference. The first thing you're going to do is make a skeleton structure of the molecule. The atom that can make the most bonds, and this is usually the least electronegative atom, not always, but it's usually, so the atom that can make the most bonds will go in the middle, and then we're going to put all the other elements around it. Your rule here is you cannot put hydrogen in the middle. Never, never, never put hydrogen in the middle. It can only make one bond. It would be a very bad central atom. Okay? So you're going to make your skeleton structure first, and just kind of, like I said, put the one in the middle, makes the most bonds, and then put the other atoms around it. Then you're going to figure out the total number of valence electrons that you have to play with in your molecule, and I will show you how to do that. Then you're going to use 2 valence electrons to form each bond in the skeleton structure. You're going to bond your outside elements to your central elements. And again, the reason it says 2 valence electrons is because there are 2 electrons in a bond, right? So we have, 1 electron will come from one atom and 1 electron will come from the other, and we share them to make that bond. And then we'll use any remaining electrons as unpaired, or we might form double bonds or triple bonds, things like that. Again, this will make lots more sense as we go through it. One last rule, though, that will make your life kind of easier is the honk rule. Hydrogen and halogens, right? Remember the ones next to the noble gases are called halogens. So hydrogen and halogens all form one covalent bond. Oxygen and sulfur and anything under that form 2. And then nitrogen and phosphorus and anything under that form 3. And carbon and silicon and anything under that will form 4. So, it's kind of working backwards. If we look on the periodic table, like the halogens, then oxygen and nitrogen and carbon, right? That's how many bonds they can form on the periodic table. So this will help you out if you're ever, in a jam or you can't figure out how many bonds something should be making. Try and follow this honk rule. Let's try this out. So we are going to try and draw the Lewis structure for phosphorus trichloride. And so the first thing that we'll do is, figure out our arrangement of atoms. Figure out which thing we are going to put in the middle. So our options are phosphorus or chlorine. So the way that we determine which one goes in the middle is we will look and see which one can make the most bonds. So again, by following the honk rule, right? If we think about our honk rule, 1, 2, 3, 4. Phosphorus on the periodic table falls under nitrogen. Okay, so that means that phosphorus can make 3 bonds. Chlorine is a halogen, so that will go with H. That means it can only make 1 bond. So phosphorus will go in the middle because it can make 3 bonds. So again, the one that can make the most bonds will go in the middle. Another way of looking at this is to put the one that is the least electronegative in the middle. So that would be phosphorus because it's farther away from fluorine. Sometimes that one's a little bit hard to see. So this honk rule is a really good way to just figure out, which one goes in the middle. So we put phosphorus in the middle. So this is our, what's shown below. Phosphorus will go in the middle, and we've put the 3 chlorines around it. Again, this is because phosphorus can make the most bonds. Our next step will be to figure out how many valence electrons we have to use. So phosphorus, right, if we look on our periodic table, phosphorus is a group 5A, which means that it has 5 valence electrons. So we're getting 5 valence electrons from the phosphorus. And then chlorine is in group 7A, which means that it has 7 valence electrons. And since in our molecule it shows that we have 3 chlorines, we're going to do 3 times 7 because each of those chlorines will give 7 electrons to our structure. So that's why we get 21 here, 3 times 7. And if we add them all up, so total we have 26 electrons that we can use in our structure for phosphorus trichloride. So here's how we figure this out. So again, phosphorus goes in the middle, like we determined in step 1, and then our chlorines were around it. And now what we do is we use electrons to bond each chlorine to the phosphorus. Okay, and so remember, in each one of those bonds, there are 2 electrons because it takes 2 electrons to form a bond. So here we've used up 2, 4, 6 electrons just bonding the chlorines to the phosphorus. So we use 6 of them up, so we have 20 electrons left, right? Because we had 26 to start with, we use 6 up bonding those chlorines to the phosphorus, so we have 20 left over. Now, what we're going to do is we're going to use those remaining electrons to complete octets. Okay, so there's the answer, but I'm gonna draw it again over here so that I can walk through it a little slower. Okay, so this is what we had from the last slide. And again, we have 20 electrons left. So each of these atoms needs to have 8 valence electrons. So right now, each of the chlorines has 2 because they're sharing the electrons from that bond. Phosphorus right now has 6 because it has 3 bonds going to it, and each one has 2 electrons. So we're going to try and finish off those octets. So we can go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Because remember, we had 20 electrons left. So now we go through and we make sure, do all of the atoms have an octet? So if we look at the chlorine on the right, that one has 1, 2, 3, 4, 5, 6, and then 7, 8. Remember, there are 2 electrons in the bond. So that one has 8 valence electrons. The chlorine on the bottom has 2, going around, has 2, 4, 6, 8. The chlorine on the left has 2, 4, 6, 8. And the phosphorus in the middle has 2, 4, 6, 8. So all of the atoms have an octet. That means that this is a good Lewis structure. This is correct. Okay, so this is kind of the thought process you'll have to go through when you're drawing these Lewis structures. Again, I'm going to do lots of examples. Sometimes you're going to not have enough electrons. So like here, I went through and I just kind of filled in all of the rest of the electrons, right? And I was able to give everyone 8. Sometimes you'll run out, right? Because we had 20 electrons we could use. But if we only had 18, I would have run out before I gave phosphorus those 2 electrons. So when you are going to run out, the way that you kind of solve this problem is you form things called double bonds and triple bonds. In a double bond, you have 2 pairs of electrons that are being shared. And in a triple bond, you will have 3 pairs of electrons that are being shared. So my examples to those will come in our example problems. So let's try and draw some. So the first one is methane, CH4. So following the honk rule, right? 1, 2, 3, 4. Carbon can make 4 bonds. Hydrogen can only make 1. So carbon will go in the middle, and we'll put the 4 hydrogens around it. Then we need to figure out how many electrons we have to use. So we'll have carbon plus 4 times hydrogen. So carbon has 4 valence electrons plus 4, and each one of those hydrogens has 1 valence electron. So we have 8 valence electrons that we can use in our structure. So the first thing we always do is we go and we connect all of our exterior atoms to our central atom. So we go like this. And when we do that, remember, each one of those bonds that we're forming holds 2 electrons. So this is 2, 4, 6, 8 electrons that we've used up. So we had 8 electrons to use. We've used 8. We're left with 0. So we better hope that everything has satisfied their octets and duets. So remember, hydrogens, their, quote unquote octet, their duet is complete when they have 1 bond going to it because they only need those 2 electrons. So if we look, each one of our hydrogens has 1 bond, which means it has 2 electrons. So all of hydrogen's duets are filled. So hydrogens are good to go. And then we look at carbon. Carbon needs to have an octet. It needs to have 8 valence electrons. So it has 2, 4, 6, 8 electrons going to the carbon. So carbon's octet is complete, which means that this is a good Lewis structure. Let's try another. Chlorine, Cl2. So here, when we draw this structure, because, there's only one type of atom, right? There's only 2 atoms that are going to get bonded together. We don't have to go through and determine which one goes in the middle because they're just going to sit side by side. Then we have to figure out how many valence electrons do we have to use. So we have 2 in however many chlorine has, right? Which means 2 times 7 because chlorine has 7 valence electrons. So we have 14 electrons that we can use in our structure. So again, the first thing that we're going to do is we're going to bond them up, right? Connect them together. So when we do that, we use 2 electrons in forming that bond. So I'm going to go 14 minus 2. So I have 12 electrons left that I can use. So we can go around and give them an octet. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So now I've run out of electrons, and so we hope, right, that both chlorines have an octet. So the chlorine on the right has, 2, 3, 4, 5, 6, 7, 8. So that chlorine's good. Chlorine on the left has the 2 from the bond. 3, 4, 5, 6, 7, 8. So both chlorines have 8 valence electrons, which means that this is a good Lewis structure. Let's try water. So water, right, we need to figure out what goes in the middle. So the one that goes in the middle, right, we follow the honk rule. So here, if we're looking at this, hydrogen can only form 1 bond, but oxygen can form 2. So oxygen will go in the middle of our structure, and the hydrogens will go on the outside. And I want to be really picky about something. I'm not going to be picky about a ton of things, but I want to be really picky about the way that you draw water. Because the way that you draw water has a lot to do with water's properties, and it's a really good habit to get into. So if we think about drawing the dot structure for oxygen, right? Oxygen has 6 valence electrons. So when you go 1, 2, 3, 4, 5, 6. So when I do that, you'll notice that the 2 sets of lone pairs, end up next to each other. And the 2 bonding electrons will end up next to each other. So that's why I've drawn the hydrogens where they are, right, to the left and down, because they need to be next to each other. There's no way, if you draw your electrons in a circle around oxygen, right, doesn't matter where you start, if you draw 6 electrons in a circle around oxygen, the 2 lone pairs will always end up next to each other, and the 2 bonding electrons will always end up next to each other. There is no way that if you follow those rules, you will end up with the lone pair split. When we get a little bit farther into chapter 11 here, or 10, sorry, a little farther into chapter 10 here, we will need these electrons to be, next to each other like this, to talk about the shape of the water molecule. If you draw it correctly, then this shape will end up being what's called bent, and this shape will end up being what's called linear. And if you draw it linear, you will assume all kinds of things that are totally wrong about water. So make sure you always draw, you'll always have your lone pairs on your oxygen next to each other. So anytime you draw oxygen, put the lone pairs next to each other and the, bonding electrons next to each other. So that's my one random thing I'm going to be picky about right now. So that's why I have hydrogens, because I see that this is an oxygen, so I know that the 2 things that are bonding are going to go next to each other rather than across from each other. So again, that's kind of a nuance that I want you to pay attention to. So now we need to go through, figure out how many valence electrons we have to use. So we have 2 hydrogens plus our oxygen. So we have 2 times each of the hydrogen has 1 valence electron plus the 6 coming from oxygen. So we have 8 electrons to play with. So again, the first thing we're going to do is we are going to attach our exterior atoms to our central atoms. And we do that, we use 4 electrons. So we've used 4, so we have 4 electrons left. Now, the hydrogens already have completed their duet because they made one bond, but we have to finish our octet on oxygen. So we go 1, 2, 3, 4, right? And so that used up all of our electrons. We used them up, we have none left. And so we go ahead and make sure that oxygen has an octet, right? So it's got the 4 electrons that we just added, and then 6, 8. So oxygen has an octet. That is a good Lewis structure. Let's try a little bit trickier one. So this is carbon dioxide. And so we figure out which thing goes in the middle, just like normal. Follow the honk rule. Since carbon can make the most bonds, right? Carbon can make 4 versus oxygen that can only make 2. Our carbon atom will go in the middle. And then we're going to put the oxygens on either side. So I'll put them across from each other because it's only when oxygen is in the middle that we need to do that weird bend, right, to make a bent molecule. Carbon being in the middle is totally fine. We can put them on either side. So then we figure out how many valence electrons we have to play with. So we have carbon plus 2 oxygens. So carbon has 4 valence electrons plus 2 times 6 from each of the oxygens. 2 times 6 gets us 12, plus 4, we have 16 electrons to work with. So again, our first thing we're going to do is we are going to bond our oxygens to our carbon. So when we do that, we use up 4 electrons. So we have 12 electrons left to use. So now, if we were going to go through and do what we did before, right, we would go, okay, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. And that would be all of the elements have an octet. Yay, us. But we can't use 16 electrons, right? We only have 12. So that can't work. That's clearly wrong. Okay, because we can't use 16 electrons. We can only use 12. So there's got to be a different way to do this. And so what I was alluding to before is that when you're going to be short on electrons, the way that we solve this problem is we make double bonds. So here's what I'm going to show you how to do this. So we have 12 electrons left. So let's say we gave each of our oxygens an octet. So I put 6 more on that one, 6 more on that one, and my 12 has now been used up. Okay, each of the oxygens right now has 8 valence electrons, which is lovely, but the carbon in the middle, poor carbon, only has 4, right? It has 2 from each of the bonds. So this is not a good Lewis structure because carbon's octet is not satisfied. So the way that we solve this problem is we have our oxygen is going to share more of its electrons with the carbon. So instead of being this lone pair on oxygen, it's going to go and form another bond with the carbon. This will be called a double bond. And so when we do that, so I'm going to draw that over here. When we do that, now carbon has 6 electrons around it, right? 2, 4, 6. And each of the oxygens still has 8. So this oxygen on the left, even though it moved those electrons, right, and shared them with the carbon, it still has 8 because it has 2, 4, 6, 8, which is great. However, carbon still only has 6 electrons. It needs to have 8. So the other oxygen is actually going to do the same thing. It's also going to donate some of its electrons to the carbon. And when it does that, it's going to make a structure that looks like this. All right, so now this structure that I have over here on the left, each of the oxygens has 8 valence electrons because it has 2, 4, 5, 6, 7, 8. The other one has 2, 4, 5, 6, 7, 8. And the carbon in the middle has 2, 4, 6, 8. This is our correct Lewis structure for carbon dioxide, okay, because it satisfies all of the octets for all of the elements. Okay, and, right, it stuck to our limit. We only had 16 electrons total that we could use, and there are 16 electrons total in that structure. So make sure this counting up electron step is really, really important, because otherwise you might draw something like this one, which would be totally wrong, right? Because you used up electrons that you don't have. So make sure that you go through and you count your electrons. So these sets of double lines here, those are called double bonds, right? And so in those double bonds, there are 4 electrons total being shared, right? 2 electrons in each bond. And so these are shorter and stronger than single bonds because there's more electrons that are being shared between the atoms, which I think naturally would you would think that they would be stronger. The reason that they are shorter is because you can kind of think of it like magnets, right? More electrons in the middle draws the nuclei of these atoms closer together and makes that bond shorter. So double bonds are stronger and shorter than single bonds. Let's try another one. NH3. So again, following our honk rule, right? We figure out, okay, what goes in the middle? So nitrogen will go in the middle because it can make 3 bonds and hydrogen can only make 1, right? We never put hydrogen in the middle. So nitrogen will go in the middle, hydrogens go around it. Then we go through and count up how many valence electrons we have to use. So we have nitrogen plus 3 hydrogens. So nitrogen has 5 valence electrons plus 3 times 1 from each of those hydrogens. So we have a total of 8 electrons that we can use in our structure. So we're going to use up some in bonding, right? 2, 4, 6, right? So we used up 6 electrons connecting those hydrogens to the nitrogen. So we have 2 left. The hydrogens are all satisfied, right? They all have 1 bond that completes their duet rule. So these 2 electrons will go on the nitrogen to finish off its octet. So now we double check, make sure nitrogen has 8. 1, 2, 3, 4, 5, 6, 7, 8, right? Nitrogen has 8 electrons, which makes this a good Lewis structure. Let's try another. Oxygen, O2. So again, this is a diatomic. There's not going to be like a central atom, so we're just going to put these oxygens next to each other. Okay, to figure out how many electrons we have 2 oxygens, right? So we have 2 times 6, so we have 12 electrons to use. First thing we're going to do is bond them together. So those 2 electrons are done. We have 10 electrons left. So now we go and try and complete the octets. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Right? And I used up 10, so I have to stop. So if you'll notice, the oxygen on the right has 8 electrons around it, right? 6, in the lone pairs and 2 in the bonding pair. But the oxygen on the left only has 6 electrons. 1, 2, 3, 4, 5, 6. And so it has an incomplete octet. Again, like we talked about in carbon dioxide, the way that we solve this problem, right, when we're going to run out of electrons, is we have one of our atoms donate some electrons and share them in a bond instead of having a lone pair. So when it does that, now it looks like this. Okay, and so we double check, make sure that each atom has 8 valence electrons. So in the oxygen on the right, we have 2, 4, 5, 6, 7, 8. So that one's good. Oxygen on the left has 2, 4, 5, 6, 7, 8. So this is our correct answer for our Lewis structure because that gives each atom a complete octet. Whereas this one over here on the right, on the left, the oxygen on the right had 8. The oxygen on the left only had 6. So it's a bad Lewis structure. Okay, so always, like I said, make sure to do this electron count because otherwise you'll just go filling in electrons that you don't necessarily have access to. One more, last one. So this is nitrogen. So again, we're going to, put it side by side. And we figure out how many electrons we have to use. So there are 2 nitrogens. So we have 2 times 5 valence electrons. So we have 10 electrons to work with. First thing we're going to do, we're going to bond them together. So we subtract out 2. Now we have 8. So we go, okay, 1, 2, 3, 4, 5, 6, 7, 8. And I ran out, right? Can't use more electrons than I have. So the nitrogen on the right has a complete octet, which is great. But the nitrogen on the left only has 4 electrons. So this is definitely not a good structure. We do not have a complete octet for that nitrogen on the left. So if we donate one of our lone pairs, now it would look like this. I'm going to move those electrons a little bit. So if we look, the nitrogen on the right still has 8, right? 1, 2, 3, 4, 5, 6, 7, 8. The oxygen on the left has 6. 1, 2, 3, 4, 5, 6. So this is still not a good Lewis structure because the nitrogen on the left still doesn't have enough electrons. So we're going to move yet another lone pair in there to be shared. So now it would look like this. All right, so now we go through and we make sure, okay, does it have 8 now? So the oxygen on the right has 2, 4, 6, 7, 8. The oxygen on the left has 2, 4, 6, 7, 8. So this is finally our correct Lewis structure because both atoms now have 8 valence electrons. So this is a little bit tricky. But again, if you get to a situation like this and you run out of electrons, start forming double bonds and triple bonds so that you can make your correct Lewis structures. So like I was talking about before, the more bonds you have, the stronger those bonds are. So like double bonds are stronger than single bonds, and triple bonds are stronger than double bonds. And this is because more electrons are being shared between those atoms. There's more attraction holding those atoms together. And the more bonds you have, the shorter those bonds are. So double bonds are shorter than single bonds. Triple bonds are the shortest of them all. And again, this is because, more electrons being shared between those atoms will create more of an attraction to the nuclei of the bonded atoms, drawing them in closer. If I ever put on a quiz question or test question about quadruple bonds, know that I am pulling your leg. There's no such thing as quadruple bonds, and I'm just trying to see if you're paying attention. So that's that. Go ahead and pause here. We do have a little bit more. Pause here and try and do lecture worksheets problems 1 through 10. So this is on drawing Lewis structures. You need to draw lots and lots and lots of Lewis structures to get lots of practice. This is one of those things where the more you practice it, the better you will get at it. So make sure to do tons and tons and tons of practice. Once you do what's in the lecture worksheet, I would go find even more problems. So go ahead, pause here, and then resume when you're ready to continue. All right. One last topic for today is how to draw the Lewis structures for polyatomic ions. So this is a little bit different. It's not a lot of bit different, but it's a little bit different for these polyatomic ions because they are charged. So let's go through the process. So if we think about the Honk rule, right? Nitrogen versus oxygen. So nitrogen will go in the middle because it can make the most bonds. And then we'll put our oxygens just kind of on the sides. So now we figure out how many electrons we have to use. This is the part that's different. So we have nitrogen plus 2 oxygens plus, do you see this charge here, right? The charge, the NO2 minus, that's telling you, right? That negative charge is telling you we have 1 extra electron. Remember, I know this sounds silly, but electrons are negatively charged. So if you have a minus on your polyatomic, that means you have 1 extra electron to use. Or if it was 2 minus, you would have 2 extra electrons to use. And the opposite is also true. If it's at a plus, if it was like NH4 plus you would have one less electron to use because your polyatomic has lost one. Okay, so that's what these are, that's what these charges are. This is where the difference is. So we would have 5 electrons from the nitrogen plus 2 times 6 from the oxygen, plus again that one extra one from that minus charge. So 2 times 6 gets us 12, plus 1 is 13, plus 5 gives us 18 electrons that we can use. So the rest of the process is the same. So we're gonna, use our electrons to bond our exterior atoms to our central atoms. So 2, 4, so we have 14 electrons left. So let's go ahead and give everyone some electrons. So we've got, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. All right, so now that we've done that, we go through and we check and make sure that, everything has an octet. The oxygen on the right has 1, 2, 3, 4, 5, 6, 7, 8. The oxygen on the left has 1, 2, 3, 4, 5, 6, 7, 8. The nitrogen in the middle, though, has 2, 4, 5, 6. So the nitrogen in the middle is short some electrons. So again, the way that we solve this is we have one of our oxygens donate some electrons, and make another bond. It does not matter which one you pick. Doesn't matter even a little tiny bit. Hang on one second. Because the oxygens are identical, it doesn't matter which one we pick, and we'll actually have more on that later. But let's just say the oxygen on the left was the one that donated the electrons. That would mean our structure looks like this. All right, so now our oxygen on the right still has 8. Our nitrogen now has 2, 3, 4, 5, 6, 7, 8. And our oxygen on the left has 1, 2, 3, 4, 5, 6, 7, 8. So this is a good Lewis structure. Just one last step. Do you remember back here, right? NO2 minus. We need to show in our structure that we added on an electron because of that negative charge. And the way that we show this is we put this whole molecule in brackets. Okay, and then we put the negative on the outside. So those are the two things that are different for the polyatomics. For the polyatomics, you need to take into account that you get an extra electron or 2, or you lost one, or whatever the charge tells you to do, right? This is taking into account the charge. And the other thing that you need to do is you need to add these brackets to show that this is a charged species. Okay, so we draw our Lewis structure just the way that we normally do, and then we'll put it in brackets and put the charge from the polyatomic on the outside. And that's just showing, okay, guys, there's one extra electron in this structure, that's not coming from those atoms, from the valence electrons of the atoms. So now I would like you to pause again and do problem 11 in the lecture worksheet. There are 2 different polyatomics that you're going to try and draw there.